Welcome to Hood Engineering Solutions. So today we said we are going to finish up with the power distribution and consumption. We are going to mainly concentrate on the distribution side and the consumption side. Thank you everyone who has joined. So today we have our last lesson about power distribution and consumption. We learned and we started from the point of power generation to the point of transmission. Then here we are to the point of distribution and consumption. Distribution simply means the transfer of power from one common point and then channeled to different points. That is what I'm going to illustrate here. So if I would have my power lines coming through, let me say these are transmission lines. If I can have them here and then have my transformer here, and then assume this is my sub station, like that, I can be able to connect my power there. Then from this substation here I should have one big power transformer, like that. So these are incoming lines from the grid, maybe let's say that 3 kV. So this power transformer transforms voltage and also current. Remember it's rated in MVA. MVA is a megavolt ampere measurement and is voltage times current. So this transformer is a power transformer, and this one is able to give very high power enough for distribution and consumption. So from this transformer here we can be able to tap multiple outputs so that we can feed them to different points. So what I'll do here, I'll illustrate how we tap this power from this substation transformer and then distribute it to different points. So This incoming lines, remember we said here before we have this point, all these conductors getting into the transformer, we need protection. We need protection to be safe when using our power. So I will demonstrate how we do this in a quick diagram here. So if I have this as my power transformer, that is the substation. If I have this that 3 kV getting in from this point, I can be able to give different outputs like this. So this can be my incoming and these are outgoing. So you can see in, out, out. So in this substation we have transformer that is able to give different power lines at very high kilowatts, so that we can be able to share it between the numerous number of consumers. Thank you everyone for joining in. It's a good time to have you in this class. So after this distribution is done, we need to have, remember this is delta. Delta means we don't have a neutral. So what we do, we put this in something called a distribution transformer, like this. So this transformer is able to enter 3 wires and produce 4 wires. 1, 2, 3, 4. This now is 3-phase and neutral. This is line 1, line 2 and line 3. So this now power is consumable to anyone who is in need of power, either domestic or electrically. So this is 415 volts British standard, but 240 V line voltage and 240 phase voltage. So from my setup, you can actually see I have incoming into the substation. I have the distribution, the power transformer in the substation. That is delta. It means no neutral point. Then this distribution transformer enters 3 wires, outputs 4 wires. Now this power is what you see in your neighborhood or in your premises or anywhere we have high power requirements or where high power is needed. If we come to this other side, we can also have another distribution transformer just like this one here, which now also gives 4 wires. Remember we have said this and this here. If you put 2 pointers between these 2 lines, that is L1 and L2, you will see 415 volts. That is 3-phase. But if you put your pointer here and then neutral, you will get 240 volts. This is called phase voltage, this is called line voltage. So this power now can be branched into different sections, then you can tap it and then feed into different lines as you continue to distribute it. That is what we call power distribution. If you can see the diagram there, we have the power transformer that gives output to distribution transformers 1 and 2. You can find this in the power stations. Then from there, you can now, in the neighborhoods, not the power stations, in the neighborhoods, so that you can have now your power drop. You can either choose to have base voltage of 240 or 415 volts depending on your power demand. Most industries, they have their own transformers. What they do, they tap this power here from the substation, and now they include their own transformer here. This now can go to industry. So industries can use separate line and separate transformer from other consumers. So I'll just simplify my diagram so that you can see the distribution part of it, right from where we have the power transformer to where we have the distribution transformer. I'll indicate what's the in between there, and I'll give the dropping requirements for consumer service. Thank you everybody who has joined in. Remember, you can like my page, subscribe, follow. You can also hit that like button. Please give me those flying hearts. I'll appreciate so much. So from the substation here, you have seen we can have, let me assume these are my distribution transformers, and this is the substation or the power transformer. So then I can move these power lines like this. So what I'll do, if this is the transformer in your neighborhood, this should rate something like 33 kV stroke 415 or 0.45 kV. This is the primary voltage or the input here that we now tap from our distribution line like this, and now we feed it to our distribution transformer. So this 33 kV and this 0.41 kV means the input on the primary side is 33 kV, but here on the secondary we have 415 volts and it has a neutral. Now these are the 4 wires that you see running on the streets, and this is where now you get, assuming your house is somewhere here, let me assume that's my house there. What we do from these 3 lines, we actually tap this neutral. If these are the live lines like this, we tap one and feed it to your house together with neutral like this. So here we have 240 volts that you receive in your house. So in case we have an industry here, let's say we have an industry like that, then we will tap these 3 phases like this, and neutral, and then we are going to feed them to this company here, or this factory here, plus this neutral. So you can see in this is the low power consuming factories, we can have 415 volts. Then in homesteads we have 240 volts. Remember, this is the distribution to power from distribution transformer 1. In this line along the substation distribution, we can also tap like that. And then have another transformer there. That is another distribution transformer, of which now you can also have more outputs. That is line 1, line 2, line 3, and neutral. On the same line, you can add another transformer here. Like that. So you can generally see these transformers are actually tapped from the major distribution line from the substation there. So this substation here is able to give power to all these 3 transformers, and these 3 transformers can be able now to distribute this power evenly, and the total amount of power in these 3 transformers must not overload that substation transformer. So up to this point, I hope now you are clear. These are the transformers you find in your neighborhood. When you get out on the streets, you will find 4 wires along the street. That is where your power is tapped. That is called power distribution. When it gets to consumption, that is where we get now into the individual consumption and metering of the system. You guys, if you have some questions about distribution, let me see. If you need me to go into details about this, let me know. Give me likes. I would like to see those hearts flying. I would appreciate so much for your support. Getting motivated to give you the best of the content I may be able to make and give to you. So these transformers you'll find are majorly connected to one source or one supply that is able to give power to all of them. Maybe this could be, if this transformer here entered maybe something like that 3 kV, then you can be sure this line here can give something like 12 kV, can be 6 kV, can be 3 kV, in the multiples of 3. So these transformers can be able to handle this voltage and give 415 volts line voltage and 240 volts phase voltage. So now remember, in this distribution line we need to have protective gadgets. Now our protective gadgets must be able to protect our transformers and must be able to protect our power line. So I will be able to indicate what kind of gadgets we use to safeguard our distribution systems. So thank you guys for all you have joined in. I am very grateful about this. So this being our distribution line, first of all we need to have an isolator. This isolator is on your switch. That can be able to cut power to these transformers. Let me use a schematic diagram, assuming these are my distribution transformers, distribution transformers, distribution transformers. So we need these isolators to be able to actually give a connection or a disconnection place for our circuit whenever we need to do maintenance to these transformers or something like that. So here we can have these connections into the transformers like that. So now, as you can see, when we have our power input or our supply here, this is the symbol of an isolator switch in my schematic. So if we cut off this power, we will cut power to all these transformers. These transformers are high wattage transformers or high power transformers that carry a lot of load like this, so it's not safe to abruptly put them together on at once. So what we do, we include more isolators on each transformer input, so you can have individual isolators for every transformer like that. So after now disconnecting this, you can disconnect also this so that you can independently switch on the transformer after you are done with the service. Then we need to protect our, remember this is for manual switch off. Then we need to protect our circuit from something called surge. Remember, let me use one distribution transformer to illustrate this. There is something called power or voltage surge. This is when we have overshooting of voltage on the line. So remember, this line here is voltage, it's rated maybe 12 kV. We don't want in any case to have 15 kV or anything more than 12 kV. So what do? We include gadgets that ensure we don't have any voltage surge, and one of the things included are called arc horns. What are arc horns? In the transformer, let me draw a 3-dimensional diagram like this. So in the transformer, we have connections like this, and we also have connections that now come here. Let me make it better. So now, assuming this is my primary side or my supply, and this is my output of the transformer. So before now we put our supply or we connect our power to this transformer, here around these bushings we have high voltage bushes that actually look something like this. I hope I'll be able to be understood. I'm trying to draw the high voltage bushes. Thank you for joining in, whoever has joined in, whoever has liked this content. Thank you for joining in. So we have high voltage bushes. I'm still trying to draw them for you to understand. These are the ceramic insulators that are found on the high voltage bushes. Now, assuming this is the surface of my transformer, let me draw the third one for convenience. Like this. So if these are my high voltage bushes, we actually put something. Remember, this is the surface of the transformer and it has earthing like this. So this earthing should be always connected so that we can use it for safety with our arc horns. So we have this horn here. Remember, the high voltage here will be connected there. So this high voltage can be regulated using this horn. That is, if here is 12 kV, the distance between this grounding and this horn, remember, here is 12 kV and here is 0 volts. So if this voltage exceeds the rated voltage, there will be an arc here. This thing will arc somewhere there. So what happens is that when this arcing happens, it will break the fuse. Remember, here we must provide a fuse when installing transformers. That is why you see the fuses, so that they can respond when the arc horn is shorting or this voltage is somehow leaking to the ground, and this is achieved by application of these arc horns. This thing here is what we call the arc horns. Its purpose is to produce an arc when the voltage goes up more than the rated value, and this one gives the effect of leakage and it shorts to break the fuse, hence cutting power coming to the transformer, and this is how we protect our system against over voltage. So we have said these arc horns here are the ones that we primarily use for our primary surge protection. So always be aware that these are not just iron rods or something like that. These are very important rods. So with that said, guys, now we can move to the last part, that is power consumption. Power consumption is the utilization of electrical power, that is using machines, lighting, or any other use. And now we are going to be seeing different loads that we use in power consumption. We have types of electrical power loads. Remember, when you go to the market, you usually see street lights. When you go to industries, you see motors. When you go into the houses, you see lights and the like. So what we are going to learn today is types of electrical loads. One is domestic loads. Domestic load. Then we have two is industrial load. Then we have number 3, traction load. Number 4 we have, let me not use the word lighting roads, let me use municipal load. If you have any other type of electrical load, let me know, but these are the major types of loads you will see in electrical consumption. Municipal loads, this is something like street lights, we have like the city clocks, etc. These are roads that you usually see on the streets, but they are not actually owned by somebody in person. Then traction roads means things like electric trains and any other vessel that use electric means of transport to commute. These are some of examples of loads you can term as traction loads. Then industrial loads you have used in factories or industries. Then we have domestic roads. These are used in homes. So you can actually see the different types of load we have. So this is the types of loads that are majorly used in power consumption, and this is where you will be actually seeing the building of the selling companies, the power selling companies, mostly coming from these sources or these kind of loads. So we shall be going into details upon about each of these loads, that is separately, but for now my interest was just to make you understand the distribution and the consumption of load. Now at least I'll show you how we can be able to determine how much load is being used and how much bill should be paid from these consumptions. So we can go to billing. So billing is payment calculation of consumed power. So payment calculation of consumed power is done through metering. Metering from the word meter, and for this case we use energy meter, and power is measured in kilowatt hours. So in every metering gadget you will find a unit kilowatt hours. That means 1000 watts in 1 hour. That is 1 kilowatt hour. So for example, if you are using 100, let's say for example you are using 100 watts, it means you will require 10 hours to reach 10,000 watt hours. So it's 100 watts times 10 hours, that gives you 1000 watt hours. But remember, this is watt hours and we need our answer in kilowatt hours, so we divide in by 1000 to give us 1 kilowatt hour, and this is the unit that counts on your meter reading. So if you are using gadgets of 100 watts in 10 hours, that is when you pay 1 unit of your token. So we can have a few more examples. For example, if I'm using 50 watt load, how many hours will make 1 kilowatt hour unit? So if I'm using 50 watts load, that is, let's say for example I have lights that are 50 watts in total. So how many hours will make 1 kilowatt hour? I hope you can see my question there. If I have 500 watts load, how many hours will make 1 kilowatt hour? So what we do is 1 kilowatt hour is equals to 1000 watt hours. So if I have 50 watts, I will be able to use it X hours to give me 1000 watt hours, like that. So my X hours will be 1000 divided by 50. So we can have 20. So X hours equals 20 hours. So I'll be required to use my 50 watts load for 20 hours before it gets to 1000 watt hours or 1 kilowatt. So if 1 unit is equals to $2, like that, if my 1 unit is $2, then after 20 hours I'll be able to pay $2 for my 1 kilowatt power. So bill per month So in order to calculate my bill per month, I'll be able to know my total load, like that. Then I'll be able to know how many hours of consumption So if you have the total load at the number of hours of consumption per day, you can actually, to get your monthly bill, you can actually calculate the total power times hours of consumption, like that, per day, or in 24 hours, then times 30 days. So for you to get your total bills, you have to know the total load in your house, the number of hours you are using the load, and then you multiply by 30. So giving an example, if I have 50 kilowatts, 50 watts load, and I'm using it 10 hours per day, then it means I'm using 50 times 10, which is 500 watts per day. That means I am using 0.5 kilowatts per day, like that, which is in 10 hours. So if I'm using 0.5 kilowatts per day, it means it's 0.5 kilowatt hours, because we are multiplying by the number of hours in the day that I'm using it. So if I need to count my monthly bill, will be 0.5 kilowatt hours, that is per day, times 30. This one gives me 15 kilowatt hours. Now 15 kilowatt hours is what I'm going to be charged for. So if 1 unit or 1 kilowatt hour is equals to $2, so my total bill will be 15 kilowatt hours times $2. This one will give me $30 per month. So basically, that is how we calculate consumption of power, and that is how we give the readings on the consumption point. Remember, this is on the consumption point. If we need to know how much power we are getting or we are distributing in one street, we need to put metering gadgets on the street and in the substation, so that we can easily monitor the consumption. So if you like my classes, guys, you can like my page, you can follow, subscribe, comment on all my socials at Wood Engineering Solutions. Until the next class, we are going to learn about our second power generation method. Thank you, guys.